Hello, everyone. Welcome to the NAA webinar. We're just going to wait a few minutes and let everyone get logged in, and then we'll get started. If you're just joining us, welcome to the webinar. We will get started in just a couple minutes. Okay, we still have a few people logging on, but I'm going to go ahead and get started. So welcome to the Natural Areas Association 2021 webinar series. I'm Maura McGinty-Kloss, and I am the NAA's Programs and Communications Manager, and I'm delighted that you're joining us today. The purpose of NAA webinars is not just to convey information, but to engage natural areas professionals on topics of interest that highlight emerging science methodologies and best practices. I encourage you to participate in the webinar by posting questions and comments in chat, and we'll address as many as we can. I'll be monitoring chat and we'll post the questions at the end of the webinar to our speakers. If there's a future topic that's of interest to you, please don't hesitate to let us know. Just email us at info@naturalareas.org. All right, went too fast there. So I just want to tell you a little bit for those of you who are new to the NAA. We are the Natural Areas Association is a nonprofit membership organization dedicated to the support and advancement of natural areas professionals who protect biodiversity through science-based conservation, stewardship, and advocacy. We are an engaged community of peers and colleagues who form a resource for one another. We can respond to each other's questions, propose ideas, share best practices, and advance methodologies through communication. We've been doing this work for over 40 years, and you can engage with the NAA in a variety of ways. We have our Natural Areas Journal, which this webinar was born from 2 articles. And we have stewardship and action field workshops. We have these monthly webinars. We also host our State Natural Areas program, and the next one for those of you who are State Natural Areas managers is August 10th. So I encourage you to check out our website. It's the role of groundwater in natural area stewardship is the topic. And then I just want to highlight some of our upcoming webinars. So in August, we'll be talking about priority species lists to restore desert tortoise and pollinator habitats in the Mojave Deserts and shrublands. And then we will be skipping September just because this is a busy time of year for everyone. We'll have another webinar in November using informed plant selection to restore pollinators and songbirds in human-dominated landscapes. And then in October, we will be hosting our second virtual Natural Areas Conference. This will be a one-day virtual event, and the topic is Life from the Ashes, exploring the impact of prescribed and natural fire on insects and other invertebrates. And this topic actually came from our February State Natural Areas program, when so many of our land managers were talking about this issue and some of the things that they've been learning about it. So we hope that you'll join us. And on a related note, one of the things we do at the National Natural Areas Conference, sorry about that, is we give 2 awards. And the call for nominations for these 2 awards is open through August 5th. And so I just want to encourage you to think about colleagues you have who operate with excellence or have great achievements in their career. So we have 2. One is the George Fell Award, and that's for an excellence and achievements in the course of your career. It could be through science, through research, through a variety of things in the protection of the biodiversity of our natural areas. And then the Carl Becker Award, which is particularly focused for land managers, stewards of our natural areas and preserves and parks and wilderness. So put your thinking caps on. If you've got somebody you'd like to nominate, please go to our website and fill in the nomination form. It's very brief, but we would love to hear from you. And then just wanted to let you know, if you're not a member of the NAA, You did pay to join this webinar, and you will receive a 7-day trial membership as a part of that. And during that time, you'll have access to our complete archives, which will include the recording of this video, as well as access to all the other resources that members have. If you do choose to join the NAA following this free visit, we will apply the $29 to your membership, so it's only an additional $50, and then you can attend all of our webinars for free. So it's a good bargain. All right, so now let's get to our topic today. We do have two speakers. As I mentioned earlier, they both wrote articles in the Natural Areas Journal on related topics and agreed to join us today to present to you. So I'm going to introduce both of them, starting with Ken Holsinger, who is an ecologist with the Bureau of Land Management in Montrose, Colorado. His work interest includes the conservation and recovery of threatened and endangered and narrow endemic species, rangeland ecology, upland, and riparian restoration. Ken's presentation will be on using sampling to develop more reliable size estimates for populations of at-risk plant species. And then our first speaker today will be Carlos Ramirez-Reyes. He's a conservation scientist working for the Mississippi State University. He's interested in landscape ecology, land systems, and interdisciplinary research. His work includes developing species distribution, models to inform species management, and assessing deforestation and other land use changes in Mexico. The title of his presentation will be Targeting Surveys for At-Risk Species Through Distribution Models. And I saw Carlos peep in, so come on back, Carlos, and it's go ahead and get started. And you can take over sharing the screen. There you go.
Thank you for the introduction, Moira. And thank you everybody for being here today. I hope that you are able to see my screen. Effectively, I'm going to present you the work that I have been doing for the past couple of years. However, this is by no means my work only. Is also the effort that my colleagues at Mississippi State University, Christine Evans, Garrett Street, Francisco Pilella from the Mississippi Cooperative Fish and Wildlife Research Unit, and also my colleague Todd Jones-Farran at the U.S. Fish and Wildlife Service. All of us have been working together on this project. Just before I jump in, I want to mention what is driving us to do this work. Many of the people that are in the audience are maybe familiar with the species status assessments. This is a tool that has been developed by the Fish and Wildlife Service in order to inform the listing decisions for the Endangered Species Act. This tool is great. It's a big effort to try to compile all the information for particular species that are petitioned for listing decisions. If you have seen these documents, are very comprehensive. They are very thick documents, and they explain all the different species needs for the species that has been petitioned, and also lay out what is the current species conditions. How big is the populations, where are the populations, what are the threats, and also it lays out what are the future species conditions based on different scenarios. So it anticipates climate change scenarios, development, some future trends for the species. So this document, however, despite that it's pretty comprehensive, it has a limitation that is based only on data that is already collected in known populations. Like in this case, for these mussels, we have all of these populations that have been identified, and the species status assessments is based on that information. However, we don't know if there are additional populations that have yet to be detected, and therefore we don't know how is the status of the species in those other conditions. Therefore, our goal is to develop a framework that can help us create potential habitat suitability maps that can guide additional survey efforts for at-risk species. This is, instead of having data for only the populations that we know, like the map that I'm showing you here, we can create a map that can target areas so we can survey them and maybe identify new locations, and therefore increase the robustness, the strength of these species status assessments. We have been doing this for a number of species at this point. We have been working with multiple plant and animal species. I'm going to show you only a subset of them. And I'm going to tell you only the Latin names because I'm pronounced better Latin than English. So Balduina atropurpurea, Scutularia omulgi, Rhynchospora crinipes, Torreya taxifolia. All of these species have been located in the southeastern part of the United States. And I'm going to spend a little bit of time to describe the methods because I want you to get excited about this and the somehow simple approach that we are developing. But despite that it's simple, it's robust enough that we can get a lot of good data out of that. So this is the the species distribution model method that has been going on for maybe a couple of decades. So it has already solidified. However, we believe that it is still under use. Practitioners still don't adopt this technique. The U.S. Fish and Wildlife Service hasn't adopted at its fullest. So I want to keep talking on this topic. So the basic data that we need to construct the species distribution models are the point locations where we found those species, the coordinates, the XY coordinates, and also the environmental variables that are presumed to affect the distribution of the species. It could be topography, it could be soil types, elevation, precipitation, and so on. We also need a way to relate that to these two components. We create a function that associates what are the environmental values of those locations and create a habitat suitability function. To do that, we have been using one of the three most popular algorithms to create this mathematical function. One is the GAMS, the GBMs, Maxent probably is one of the most common out there. And then we validate our models using one of the most common metrics. It's called the AUC. We use a slightly a variation of the typical AUC, the area on the receiving characteristic curve is called the precision recall, AUC. And once that we build the model, once that we calibrate it, we extrapolate into the study area that we have to predict suitability across the whole landscape. If you see it, each of these individual models is having a different prediction. And maybe you will see some similarities, some discrepancies. Areas that are darker are higher suitable. So this map is probably over predicting suitability across the landscape compared to these other two. So this is when the evaluation of each modeling algorithm comes to play. So we take into account areas on convergence. We average all of these individual maps to try to find areas of convergence. If you see all of these areas in the three models are indicated as suitable. So we want to capture that into an ensemble map that also contains that as a highly likelihood area to host conditions for the species. And you see this ensemble map also wash out all of this over prediction because this map have a lower suitability compared to the suitability scores that we obtain in these other suitability models. This suitability model, this is just a hypothetical example, will have a higher suitability, sorry, a higher prediction power, and therefore will have a higher weight in the ensemble map. One model that didn't perform very well, we want to still capture the areas that converge with other models. So we still incorporate it in the ensemble. However, that map is being penalized by having lower weight in the ensemble map. Let's see how this works in our work. These are the results for Rhynchospora crinipes, the hairy pedunculate big sage or mosquito big sage that is distributed in the southeastern part of the United States. This is the work that we published at the Natural Areas Journal earlier this year. This is a at-risk species that has been petitioned for listing decisions on the Species Endangered Species Act. And it likes to live in low streams, black water streams in the southeastern part of the United States. What we only know is the range map. However, it is a large area to cover. So we want to target areas to get more data about the species. So we walk through different agencies, different specialists to try to obtain the data about the current distribution of the species. If you see there is data in Mississippi, in Alabama, also North Carolina, and there is a gap in South Carolina, but probably the gap is actually maybe not a gap, it's just that we haven't detected the species. So we want to target areas to increase our knowledge to target the surveys. We also talked to the experts and they told us which variables can affect the species, so we compile it in the form of raster data. We then created these suitability maps using the three approaches, GAM, Maxent, GBM. If you see there are some convergences between Maxent and GBM, the pattern of suitability tends to be similar. Low suitability is in light colors, high suitability in high. GAM, it overpredicted a little bit too much. It's saying that a bunch of the landscape, not all of it, however, so it is still discriminating. However, a lot of the landscape is in the southern part, in the study area, seems to be suitable. However, it had a lower accuracy. So it will be penalized in our ensemble map, which is here, which had a higher accuracy compared to any of the three of them. So there is a value of creating the ensemble that takes the conversions of the three maps and also, is, as I say, is being penalized for the models that have lower accuracy are being penalized and not have a higher weight in the ensemble map. So let's target those areas. If we clean this suitability map showing only the areas that are more suitable, we got this other map, which seems to be more cleaner, seems to be targeting better the areas that we might investigate. And if we look at the numbers, we observe that the suitability that has more than 0.4 in this scale of suitability is only 3.2 of the landscape. So right away, we are targeting a small portion of it to do surveys. But if we look at the areas that are very highly suitable, like very, very rich suitability for the species, only 0.38%. So if we have limited resources, we can right away target those areas first and then start moving up in suitability as resources and allow us. We also identify some of the important model variables that are describing the presence of the species, like the conversions of Atlantic white cedar suitability. It seems to be like these two species like to be close to each other, particularly the big sage likes to be closer to the Atlantic white cedar, and also annual precipitation seems to be a very good predictor. I don't have time to show you the results for all the species, and also it's going to be redundant. I just want to show you that we did this analysis for multiple species. We published this work also earlier this year at the Fish and Wildlife Management, the Journal of Fish and Wildlife Management, where you can have a look at the results. I just want to reiterate that we produce for each modeling algorithm, GAM, GBM, and Maxent, one suitability map. And then we average them and weight them by the performance to create ensembles. This is the final product that we are suggesting to managers to target surveys for these species. Now, how can we use this data right away? We can use these maps to target surveys. For example, for the mosquito big sage, we know that it likes streams. And if I give you a map of the streams of the study area, it will look like this. And then the practitioners, the people that are going to the field, are going to tell me, thank you very much. I cannot go to all of these areas. But with our suitability map, we are already cleaning out a lot of the potential streams that could host the species and rank them to their suitability. So therefore, they can optimize the resources and only target those that have the conditions to host the species at the landscape level. Also, we are obtaining information about the species and habitat associations. Like some of this data has merely descriptive for people in the field, But now we have quantitative information about where the species has been located and what are the environmental conditions associated to the gradient where we find it. For example, as we mentioned earlier, the species has a more likely of occurrence if there is more habitat for Atlantic white cedar. If there is low fraction of clay in the soil, there is also more likelihood to find the species. If you are in a floodplain or in the vicinity of a floodplain, also there will be more chances to find it. And if you have low stream velocities, like these low streams that are able to concentrate tannins, actually this is species like black water streams, which are rich in tannins. So if you have low streams with low velocities, you will have more chances to develop that concentration that will promote the concentration of tannins that are favored by this species. Later on, if the species requires protection, if it passes through the Endangered Species Act and there is some measurements to try to recover populations to protect the species, we can use these suitability maps to identify possible translocation areas. We can identify, yes, we find it here, but there is also likelihood to have good conditions here. So we could move individuals to nearby populations of near to different locations to increase the numbers of the species. We can also overlay these maps with future threat scenarios. For example, maybe there are some areas that are meant to be developed or they are likelihood to be developed. So maybe we can avoid those areas and then promote conservation in areas that are not going to be impacted by future scenarios of development, maybe future scenarios for climate change or the conversion with invasive species. So there is value on creating these maps, not only for pre-delisting decisions, but also after that. I encourage you to use this type of approach for multiple species. These methods can be transferred to any species, at least terrestrial species. Maybe aquatic species will need a little bit of modification, but at least for terrestrial will work. And I want to spend some moments of my time just to tell you about our lessons, because I think that that's going to be important for you, since the methods that we have been proposing are not necessarily too novel. Species distribution models have been going on for 2 weeks, as I mentioned. However, they are not utilized or they are overseen, or maybe they are not as effective as we would like to. So maybe I want to tell you our story of what worked, so you can replicate some of the work that we did. First of all, to find a species that actually needs an SDM development. We have been partnering with practitioners that actually have need for our models. They want a model. So there is not going to be, like, we are academics, and sometimes in academics we make exercises that have value on its own, but if you have an actual use, it's even better. So all of the species have a need, and therefore we will increase reliability and the use if we work with practitioners. Another message for you: is important to co-produce these models with as many partners and experts as possible. So these are the entities that participate in our modeling exercises: conservation organizations, species experts, data providers, and our modeling team. I'm going to describe them. The Fish and Wildlife Service was our conservation organization. They identified which focal species were candidates for the models. They were following very closely the development of the models, and they were the liaison between the different participants. They helped us to organize all the different components to have everybody engaged. And also, super important, identify the funding for us to work on. Our modeling team at Mississippi State University had the technical capacity to compile and analyze the species and ecological variables, and was able to create these species distribution models. However, we also relies heavily on the species experts. All of these people that are going to the ground, that have been going to the sites, collect data, know all the ecological requirements for the species. Those were crucial for us to inform which variables we need to input into the model and then later on follow up to validate the models, making sure that what we are predicting on the computer also makes sense on the ground. Super important. And as well, having good connections with data providers. Data providers are crucial, especially for at-risk species, because we don't have a lot of data to work on. So we were trying to reach to multiple entities to gather the most data. Some of them will be the most traditional ones, like Global Biodiversity Information Facility, NatureServe. Maybe also common are the Natural Heritage Program offices in multiple states. And we also reached to not that traditional, like private companies were also investing in for some of the species and provide us with some locations in order to make our models more robust. Super important, be ahead of the game. Once that you are developing, if you are working on the species status assessments, developing a model will be too late if you are doing it in parallel with the species status assessments. We need to be ahead of the game because we need to approve the project. We need to find the candidate species. We need to find a person to work with, gather the data, check, generate the models, validate the models, make sure that we have time to refine them and disseminate them so you can go out to the field, collect more data to build your species status assessment. And ultimately, your listing decision for the Endangered Species Act. So for a couple of our species, we were a little bit too late. So therefore, our model wasn't incorporated in the work of the practitioner. But later on, we learned our lessons and we start working much earlier. And that product was ready to be used when it was necessary. I just want to summarize all of this work by saying that our ensemble species distribution models has been performed better in most of the cases in comparison to individual modeling approaches like GAN, GBM, accents. The actual ensemble will perform even better. We believe that the work that we have been doing can benefit the Fish and Wildlife Service because it can build not only before the status assessments, but also after this, the listing process. We can, and some of the lessons is that we need to prioritize those species that actually need a species distribution model. Maybe you here are very good working with GIS, and you say, I can do that. But make sure that you partner with somebody that actually needs a model, and it will be more fun and also more meaningful work that you are going to be developing. And that goes along with the co-production spirit. Make sure that you partner with species experts, species modelers, data providers. Make sure that somebody coordinates all this work because it's comprehensive. And make sure that you do all of this ahead of the time before you need the product. I just want to acknowledge the people from the U.S. Fish and Wildlife Service, field offices, all the natural heritage offices also from the southeastern region, and all the species experts from the Fish and Wildlife Service, Forest Service that have provided us a lot of expertise for our work. And with that, I will probably have time for questions. And if you want to continue on the conversation, if you're interested in our work, send me an email and maybe we can find ways to collaborate and share our work with you, our expertise. Thank you.
Hi, Carlos. So we do have some questions coming in. I will go ahead and ask one of them, and then we'll move on to Ken and we'll come back to the other questions in a minute. But did you empirically validate the accuracy of the ensemble maps? And if so, how?
We use a self-validation, so we didn't have a time. We are at the point of the project where we are giving these maps. Now, people in the Fish and Wildlife Service are doing the surveys, and now they are collecting new data that will help us to validate the models, and therefore, or also make different runs with updated data to improve the model. So we are at the stage that all the validation have been with we are partitioning our data, our training data, setting aside one set of the data and calibrating with the other set of the data. So we are at the point to actually go into the field and making sure that those models are actually working.
Great, great. So the rest of the questions I'll just ask after Ken gives his presentation. Thank you.
All right, thank you.
Okay, thanks, Carlos. Good talk. Our work focuses on sort of starting from an understanding, a very good understanding of where our species are on the landscape, and then stepping up to understanding exactly how many of those species or individuals occur on the landscape. Species I'm going to talk about today is also listed as threatened under the Endangered Species Act. And we undertook this work to also inform a species status assessment and ultimately a recovery plan for our species. I'd like to acknowledge Carol Dawson and Phil Krenning, who work in the BLM Carter State Office, of course myself, and then John Willoughby with Willoughby Ecological Consulting, the co-authors. Okay, so. So historically, population size estimates for most threatened and endangered, as well as endemic plant species, are generally non-existent or even inaccurate. Population size estimates are routinely based on cumulative results of surveys or simple guesswork. And of course, we acknowledge, as Carlos was suggesting, surveys are imperative to defining the spatial extent of a species occupation, but often lead to imprecise estimates of abundance. And this is generally because census requires a prohibitive amount of time and resources, or species detection rates are poor because of patchy distributions, low densities, or interannual variability, often cryptic phases, and responses to environmental variables. And in our part of the world, persistent drought is a big one. So the benefits of and applications of a sampling, it's efficient. It allows us to look at only a portion of the total area and make inference to the whole. It can be used for relatively small areas, a single habitat patch, an individual allotment, or a wildlife preserve, or for relatively large areas such as the species of our rare cactus, which occurs over a little more than 1 million acres. And most importantly, it's quantitative and repeatable. So again, why minimum population size? As we said, it's efficient in terms of times and resources. And when you're the Bureau of Land Management, the largest land manager in the country, resources are always limited. Allows for subjective plot placement, so we didn't spend a lot of time sampling a bunch of zeros. Results in a conservative estimate using a useful metric for conservation planning. And again, we assume the worst case scenario, the minimum amount of plants potentially on the landscape. And then it can be used for other conservation planning tools like a minimum viable population size or a population viability analysis. So a little bit of a background. The Colorado hookless cactus, Sclerocactus glaucus, was first listed as threatened under the Endangered Species Act in 1979. Initially, Sclerocactus glaucus was thought to occur in 2 distinct geographically separated areas in northeast Utah and western Colorado. Around 2009, phylogenetic analysis led to breaking up the genus or species, excuse me, into 3 separate species. The populations in Utah wound up becoming Sclerocactus Whitlandicus and brevispinus, while the glaucus association remained in western Colorado. And as a result of that work, as we currently understand it, Colorado hookless cactus is comprised of 2 population centers in western Colorado, and further genetic research is suggesting that they should be broke up even further. Those 2 distinct population centers are now being recommended to become Sclerocactus glaucus, which is, in our paper we discussed the greater Grand Valley population, and then Sclerocactus dawsonii. Dr. Mitt McLaughlin and Sammy Neubauer are currently proposing a paper to go ahead and suggest splitting them further. The bottom line is there has and continues to be taxonomic differences based on morphological plasticity, but nevertheless, the BLM as a federal agency is mandated to manage these species that have remained protected under the ESA for conservation and ultimately recovery. So a little display of where these plants occur in Colorado. So the light gray is what is currently going to be proposed as Sclerocactus dawsonii. And then Sclerocactus glaucus is the dark gray there between Grand Junction and Delta. And that's largely the population we worked on in this paper. A little bit of a biology background. The Colorado hookless cactus is limited to, again, the Colorado and Gunnison River basins and their major tributary canyons in Delta, Montrose, and Mesa counties in western Colorado. It's found primarily in small dispersed occurrences that average a couple hundred individual plants at any given site, and sometimes maybe just one or two plants. Seed dispersal is believed to be a primary factor limiting species distribution. It exhibits a bit of a generalist, it is a generalist, I should say, occurring at elevations between 3,900 and 7,200 feet. Mostly the ecological type we find it in is the Intermountain Basin's mixed salt desert scrub. It's a pretty low precipitation environment between 20 and 30 centimeters or 8 to 12 inches annually. Again, it's a generalist occupying a wide range of soil types. And plants are often found growing in unique sheltered microhabitats under and within canopy, shrubs, and grasses, which further limits detection for census. So again, we said it was listed as a threatened species under the Endangered Species Act in 1979. When the first recovery plan was completed by the U.S. Fish and Wildlife Service, there was an estimated 2,000 plants. By the 2010 updated recovery plan by Fish and Wildlife Service, there was assumed to be around 19,000 plants. And in 2017, the Colorado Natural Heritage Program, doing an element occurrence record search, suggested around 22,000 plants, with about 17,000 of those plants in the Greater Grand Valley, or now soon to become Sclerocactus area. So the other thing is in that 2010 recovery plan update, Fish and Wildlife set a benchmark of approximately 30,000 plants as a potential recovery objective. At the same time in 2010, Congress designated the Escalante wilderness area, and we embarked on some surveys in that new wilderness area to kind of understand better some of the resources in there. And we quickly showed that there were far more plants on the landscape than thought. Those surveys, we found about 25,000 plants, and in one area we found around 7,000 plants on less than 5 acres. So we quickly understood that these population estimates were way underrepresented. And further, since 2011, when I started managing this species in my field office, we've added 50,000 estimated plants through survey work. And my neighboring field office in Grand Junction has done similar additions. So in its simplest form, we took the approach of plant density times area equaling population size. We used a two-stage sampling approach. So again, we started with a good understanding of where our plants occur on the landscape. We then used a spatially balanced approach to decide where on the landscape we would go to sample. We started with 1,700 plus discrete habitat areas. And we then selected what portions of the landscape we would go sample to then do the individual population level sampling using macro plots. So a little discussion of our sampling hierarchy. Again, we had plenty of data from both the Colorado Natural Heritage Program as well as the Bureau of Land Management, but often our data were in different forms. As we said, we needed area. Many of the plant locations that BLM maintained, and to a lesser degree Colorado Natural Heritage Program, only occurred as individual points. And so we quickly saw in the landscape these distinct clusterings of plants. And so we did a GIS exercise using a density of points to generate a bounding area. One of the things that our first steps in being very conservative in our population estimate was many points that we know there are plants on the landscape did not meet the criteria for our density estimate. And so they were left out. So again, first step in being conservative is we knew many more plants on the landscape were not being included in our area calculations. So then we stepped down to our second stage of the sampling approach as we went to the sites that were randomly selected to place our macro plots. And then we established our macro plots and randomly sampled quadrats within the macro plot and to determine an estimated plant total. So at the macro plot level, we used our layout and power analysis to generate a minimum sample size. So at every one of these macro plots, we had a sampling objective that we did not want to violate. So minimum sample size was the first step in doing that. So in this case, based on the equation cited, we needed a minimum of 7.8 quadrats sampled. We sampled 8. And so at the macro plot level, we estimated 60 plants plus or minus. Just a visual image of how some of these macro plots are put out on the landscape. And for the 16 macro plots that we sampled, generated some base summary statistics, estimated number of plants, as well as a confidence level range, as well as habitat area, macro plot area, quadrat area, the total number of possible samples, and then our number of quadrats sampled little n. And that steps into getting to our density estimates. So in this scenario, we estimated 146 plants. Our macro plot area was 800 meters squared. Macro plot density is 146 plants divided by 800 to arrive at 0.18 plants per meter squared. And this is where we step into our second approach at being conservative with our population estimate. So the habitat area in this scenario is a little less than 4,300 meters squared. So when we go to do our landscape level density, we, instead of using the macro plot area, we took our 146 plants divided by the habitat area to further suppress or arrive at a more conservative plant density estimate for this particular habitat area of 0.3 plants per meter squared. So again, being conservative in that we're assuming no plants occurred outside the macro plot area that we sampled, even though we know there are often many more plants outside the macro plot area. So we can say that there is at least this many plants within this particular habitat area. So then, because our habitat areas, our macro plot areas are of various sizes, we had to use a ratio estimator proposed by Stamen and Salzer in 2001. So what this allows us to do is derive a landscape level density, determine as a ratio of the average number of plants from the collection of sample units divided by the average area of collection of sample units or habitat areas. So, and then this is our third step in, again, driving home a very conservative population estimate. We use the lower confidence level estimate of the number of plants per macro plot area to further come to a more conservative population estimate, resulting in, once you apply the ratio estimator, coming to the density by area population size at the lower 90% confidence interval, we're suggesting that there's around 103,000 plants. So our landscape level plant density of 0.061 by a little less than 17 million square meters on the landscape. And then of course, we're able to generate confidence intervals around that as well to give us our worst case scenario of around 68,000 plants on the landscape. So again, the real point I'm trying to drive home here is we know we have some statistical weakness to our approach. And that's why we were cautious at all levels to try to be conservative in our population estimate. So again, doing so, our final area of calculation is low. Recalling that our GIS exercise excluded many areas that didn't meet the density requirement, ultimately leaving out many areas on the landscape from our final area calculation. Of the 16 samples that we collected at the macro plots, it represents the minimum density of the habitat area. Again, we can say that there's at least that many plants, despite knowing indeed there may be many, many more in the habitat areas not sampled. And then ultimately, the final density estimate was biased low, using our lower 90% confidence interval instead of the estimated total for each of the 16 samples during the ratio estimation. So in conclusion, big implications for us are ultimately there are very likely many more plants than previously reported. Again, 2009, 2010 Fish and Wildlife was suggesting around 22,000 plants. Our position is that there is at least 68,000, but maybe more, around 100,000. Again, the Fish and Wildlife set a recovery goal in 2010 of at least 30,000 plants on the landscape. So it may well change the status for this species. It indeed may be less imperiled. However, with the phylogenetic work happening where the Dawsonii population may become a distinct species, it may well be more imperiled than the glaucus species. This work can be used to inform management prescriptions and actions. Ultimately, more informed environmental baselines for projects contemplated with adverse outcomes for glaucus, as well as better informed population level impacts. Ultimately, for both Fish and Wildlife Service and BLM, we believe we have more defensible decisions. We're constantly being challenged legally by environmental groups, often because of speculative data. And then ultimately far better conservation planning for the species into the future. Again, we're looking at doing a population viability analysis, and more importantly, identifying population core areas of high conservation value where we can prescribe good conservation management for those important areas, etc. And with that, I think we have time for some questions.
Okay, so let me come back on. Carlos, you're welcome to come on back on the screen. So if you have any questions specifically for Ken, please don't hesitate to put them in chat. But in the meantime, we did have several questions that came in after Carlos's presentation. And since you're both talking about modeling and sampling, both of you should feel free to jump in and provide answers. So Here's one question. Can you discuss a little bit more about environmental predictor data? And how are you determining which environmental predictor data sets you are including in your modeling effort? And then this goes on. So if you need me to come back, I can ask the questions again. Where is the data coming from? Are you deriving your own or using off-the-shelf national databases? And did you develop any Southeastern regional predictor data?
Yeah, so the work that we are doing, we are relying on already produced environmental data from national data sets. We are working on large extents, so we are projecting the distribution for this species over the whole region. So it will be a very hard work to produce ad hoc environmental variables. We are trying to use some satellite data to drive a little bit more ad hoc, like for the temporary scale that we are using, like if we are developing NDVI, we are doing our own NDVI calculations using satellite data. We're using tree canopy cover from dates that are as close as possible to the date where the occurrences were taken. However, for the majority of the variables, we are going to the national data sets, given that we don't have the effort, the time or the money to do our own data set production.
Okay. Ken, did you want to respond to that at all? You don't have to.
No, I think Carlos covered it well.
Okay. Ken, a question specifically for you, but Carlos, again, you feel free to jump in. What are your thoughts on previous counts? Why were previous counts so low? And do you have recommendations on how to use counts to assess risk and future recovery?
The first part, our counts were low simply because oftentimes our species is quite cryptic. And so whoever was there that given day mapping it made an estimate. And then the Natural Heritage Program routinely revisits some of these sites annually. And so another individual, sometimes many, many years later, also made an estimate. And one of the flaws we quickly saw is that oftentimes they may be adding those in spite the fact that temporally they're very different. And again, climate is driving our plants greatly. Who's to say the first time they were there, it was a robust year and they were abundant. And then the next time, who's to say they were there under 4 years of consecutive drought, which drives populations down. So that is the real flaw in it. Recommendations for how to use counts to assess risk and future recovery. Again, I think in the kind of work that BLM does and the Fish and Wildlife Service as well, is ultimately, you know, are we having population level effects? And so having a better understanding of how many may be in a given population area or range wide certainly informs, you know, what level of effect will that next highway project or that next oil and gas field development have? So it certainly in our minds is giving us a better assessment of the risk of, you know, approving some of these land use practices. And again, understanding where core population areas and through the land use planning process, developing strong conservation actions for those areas so that, again, the death by 1,000 cuts from proposed projects and development, we have some good, strong recovery plan or conservation actions in place to kind of say, all right, these areas are the most important of the most important, and we've got to think about placing them higher in the hierarchy of land use.
Another question, do you have any results from, and this is for either one of you, have any results from testing these species models in the field through survey work that has been informed by the models? And how did the models perform in a real world test? So Carlos, this came in after your presentation.
Yeah, I think that this is related to the first question. If we have already validated our models with empirical data, and no, we don't have that data in yet. we have for one of our species, McBride caroliniana, we have colleagues at South Carolina that are now going to the field and using our product to inform their surveys. So if we are lucky, we're going to come back in a few months with more data for us to calibrate our models, and not only to calibrate, but also to validate them. So this is unfortunately that the survey season or the field season only goes for part of the year, but we were very fortunate that we had the product right before the field season. So they are actually using our product to guide their survey. So fingers crossed that it will work for them.
Okay.
Not
So-
so much for this species. We have species distribution models for another species I manage, and it's a narrow endemic. And honestly, they've been very, very effective in field verification, and we've actually been able to add many, many new populations from well-developed models. Unfortunately, this particular cactus, being a generalist, it's been incredibly hard to develop a robust species distribution model. So narrowly endemic species, I think they're fantastic. Sometimes there's some challenges with the generalists like this particular species of cactus.
That was a very good remark, and I just want to add that the models, at least the ones that I'm producing with my team, are giving us the suitability for the habitat. So they are predicting conditions that are suitable for the species. So the maps that we are producing doesn't necessarily tell you that the species is there. So there is not a likelihood of occurrence. It's a likelihood that the landscape has similar conditions to where we have observed the occurrence of the species. So even though that we have a good map that is giving us the suitability, doesn't guarantee that high suitability areas will be populated. So there are species at risk. So they have been having a hard time to establish in some areas.
How are you communicating uncertainty, i.e. the future climate change projections, selection of predictor layers, things like that? And what insight can you take from the SDM versus where we should be hesitant?
In our case, our models are going to be good as the data. And unfortunately, it is not a common practice to report uncertainty in the data. So we are taking predictor data as a fact that is being produced on a good quality. So it's going to come with the caveat of notifying that it is going to be as good as our input data. And also, when we are creating the species distribution models in the model ensemble, we are able to make them like where the models are converging, there is more likelihood that actually the conditions are really good. So being an ensemble, you can see where all those areas overlap. So if there is a hotspot that is being flagged by multiple models, then something there should be important for the species. Whether areas that only show up in one of the models and not in the others, maybe that area was just a flag, like a caveat on one particular approach. So that is not as strong and areas where multiple models converge. So if we can indicate those areas of model convergence in the model ensemble, that also will increase also reliability on the prediction. There is a paper, and I'm gonna paste it in the chat, that tells you what are good practices to communicate your model results so they can be meaningful for practitioners. It was created by, I think it's Helen Sofer in a couple of years ago. I'm gonna paste that in the chat where you can have a look and have more ideas on how to communicate uncertainty from that paper.
Okay. One last question, because we're almost at time. For these models to be accurate, it seems like you have to have a lot of upfront data on environmental variables. What happens when a lot of this information is unknown?
That's our case. The models are not as robust as we would like to. We have models where we only have 20, 30 occurrence data. and the validation tells you those models are poor calibrated. But it still gives you a broad sense of the landscape or where your species might be found. If you have a lot of calibration data, your models are going to be more robust and probably more precise. But at least even if you have 20 or 30 calibration points, you can have a broad sense of where is the regional area where the model is capturing as a suitable for the species. More data, better products for sure.
For sure, yeah. Ken, any last comments?
No, I think not.
Okay, okay. Well, I want to thank you both very much for coming and talking. It's really an interesting topic, and heaven knows being able to do this type of modeling is the way of the future. So thank you so much. And we look forward to seeing all of you at our next webinar in August. Thank you.
Thank you.
Thanks, everyone.